start with some bookkeeping. I want to talk about limit theorems. Properties of limits. Now these are things we've been using already, and based on the steps I gave you, you kind of didn't really even have to know them, but I just want you to verify that some of the things that you find intuitive about limits are actually true in the strictest sense. At some point we have to prove them, and yeah, we're going to find that limits are actually very nice. There are very few things in mathematics that have all the nice properties that limits have, and I just want you to be aware of what they are, just in case, I don't know, you might have a problem where this is going to be important to think of specifically, although the steps we had before should be good enough. Let x approaches a, x L, limit x approaches a of g of x, n, and c is a constant. I want you to actually know how limits will actually work. And one, I want you to be aware that you can always factor constants outside of limits. So if you have the limit of a constant times a function, you can always factor that number out. And just take the constant times the limit of the function. I want you to also be aware that limits distribute across sums. So if I have two functions being added or subtracted together, and I want to find the limit of such an expression, then I can actually distribute the limits across the sum. So the limit of a sum is the sum of the limits. Now, limits distribute across sums. It's also pretty neat that they also distribute across products. So if I have the limit of a product of functions, this is going to be the product of the limits. Now that's something pretty nifty. As you are aware, not all things do both, right? So if we're talking about powers, for example, they distribute across products, but they do not distribute across sums, right? So that was one of the blasphemies, right? So I just want you to be aware, limits are actually very nice in terms of the things you can do with them. They kind of distribute whenever you feel like they should. You can factor things out whenever you feel like you should. This also applies to division, of course. So the limit of a division is actually the division of the limits. Provided you're not divided by 0, of course. And they actually go through exponentiation. And there's a more powerful property that limits have that I'm going to actually talk about here. So I have the limit of something to a power, then I can take the limit of the inside and then raise that answer to the power. And is a positive constant. It also works for negatives, but once it's negative, then you have to worry about division by 0. So just be aware that if you're applying this to a negative power, it can work. Just be sure to check that the thing is, you're not divided by 0 when you're doing it. So just wanted to make sure I mentioned those things. Probably should have mentioned it a while ago, but based on the rules that I've already given you, these kind of felt automatic, right? Like the plug-in rule for limits kind of suggested that all these things would work anyway. but I want you to specifically know that these are things that someone went through, took the time and proved. It's kind of why I know the plugin method can work when it works, and you guys should know. So limits have a lot of very nice properties, and this are just some of them. You can factor constants out, distribute across sums, distribute across products, distribute across dividends, go inside of powers. They're really nice. Very few things can do all of those all at once. So you should just be aware of that. But let's continue our discussion on continuity. I wanted to tell you some ideas and properties of continuity. We're going to do one theorem on continuity, and then we're actually going to look at limits again from a different point of view. And after doing that, we are going to start the kind of things that most people think about when they think calculus. So yeah, so by Wednesday we should start, the traditional calculus. Like very few people when they think calculus thinks computing limits. They usually think about derivatives and integrals. So let's pick up where we are started last. We saw the elementary continuous functions. There were 6 of them. I believe I asked you what they were on the quiz. What were they? 1. Yeah. Another one. Huh? Trig. Exponential functions. Rationals. Radical functions. And logarithmic. So those are the 6. Now, for a very long time, most people never actually get beyond these functions. But for a very long time, these are going to be the elements that we build up everything with. Every time I talk about a function in Calc 1, Calc 2, Calc 3, Calc 4, for a while, these are going to be the only really 6 kinds of functions that you will ever really know about, you'll ever really see, you'll ever really talk about. They build up the universe that we're playing with. So this for our chemistry class, this would be like our periodic table. These are the elements that we're working with. Everything else is going to be built up of these guys. And the rules for our reactions are our rules and formulas, and how you actually can mix these guys together, that's your algebra skills. You use your algebra skills to mix them together. But these are them. These are like the 6 infinity stones of calculus. Right? Everything you do, every time you affect reality, you are using one of these guys in a way that they all behave in particular ways, but together they can do a lot of things. And in different situations, you might want to behave like different ones of them because they're very important in that sense. So and we said these were continuous on their domain. And we also point out this is not a trivial thing. I know the plug-in rule might give you the impression that, oh, as long as you can plug in something, it's continuous, right? If it's defined, it has to be continuous. But that's not true. We looked at one example, I believe. If not, let's just look at it one another. That function, you will notice, looks like this, and the whole here looking like that. That function is defined for all real numbers. It is not continuous at all real numbers, right? So its domain is everything, but where it's continuous is not everywhere. So you can have another important function like the floor function. This is the function that always rounds down. So anytime you give it a number, it simply just cuts off the decimal point and tells you what the output is. So if you give that 2.1, it'll output 2. 3.79, it'll output 3. 17.5, it'll output 17. This is the floor function. The picture looks like this. It's also sometimes called a step function based on how the graph looks. But this pattern gets repeated, right? Every time you plug in a number, it rounds it down to the next integer that's smaller than that number. And it continues like that. This function is a very nice function, has a lot of nice examples that you can create from this function. But that's another one. It is defined for all real numbers. Clearly it's not continuous. It has an infinite number of jump discontinuities. So me saying that these guys are continuous on their domain is not just me like, well, isn't everyone continuous on their domain? No, not everyone's continuous on their domain. These guys are very special, and we can use them to build up a lot of things. And continuity is super important for calculus, so that's nice. So we know that whenever we're doing calculus with one of these functions, we can sort of breathe easier. We don't have to be as like paranoid. But if once the function gets much more too complicated than these guys, then we have to really like, be careful with something like that. So that's that. Otherwise, let's move on to some facts about continuity. These are important facts. Some of them are theorems. Theorem 1. I want to tell you about how many theorems are there. 1, 2, 3, and a couple important concepts. Then we're going to do limits. So let me just write this down. Okay. So if f and g are continuous, x equals a, and c is a constant, then following are also continuous. So these kind of introduce the algebraic functions, which are just mixtures of the other ones by arithmetic operations and composition. It turns out that if a function is continuous, any constant times that function will be continuous. If you take the sum of continuous functions, you get continuous functions. Also, if you take the subtraction of continuous functions, you get continuous functions. If you take the multiplication of continuous functions, you get continuous functions. If you take the division of continuous functions, provided they're not divided by 0, that is also continuous. So this kind of goes back to the idea that we were talking about last class when we were looking at something like, oh, sine of x over x, if x is not equal to 0 and 2 if x equals 0 or something like that. Where we could say, well, if we're not at 0, we're fine. Why were we fine? Well, because of this reason, right? Once I know sine of x is continuous, it's a polynomial. I know x is continuous. Sine of x is a trig function. X is continuous, it's a polynomial. So the division is going to be continuous whenever the denominator is not 0. So that's why I can just say, oh, we're fine. Really, it's because in the background, there's this theorem that tells me I'm fine. You know, you never really just wave off anything randomly. In math, there's always a reason why you can say something. So combinations of continuous functions like that are continuous. Continuity also plays nicely with composition. So if I have, if f is continuous at b, and the limit as x approaches a of g equals b, then if I were to take that g of x, plug into f of x, and take the limit as x approaches a, I will get f of e. So that's one important property. Here's why this is important. And you'll see me use this from time to time. Here's one way you can interpret this. Limits pass through continuous functions. What do I mean? You can kind of take the limit and move it inside of a continuous function and operate inside the function. So, for example, and again, I'm just stating these as facts, but they're theorems. You have to prove this. They all have proofs, but I don't want to spend time on these ones because I want to spend time on other ones. So, for example, if I'm talking about the limit of the sign of some function, what I can do is I can just look at the sign of the limit of the function. Right? So if the limit is outside, because I know that the sign function is a continuous function, I can actually move the limit inside of the sign function and worry about what's going inside the angle. Or if I have the limit of e raised to some function, well, that's the same thing as e raised to the limit of the function. Because I know e to the x is an exponential function and it's continuous. It's one of the basic continuous functions. Whenever I take the limit, I can move it through the exponential and just operate on whatever the exponential is operating on. So things like that are going to be nice whenever we're trying to figure something out, compute something, approximate something. You can slide your limit through continuous functions. You can move them inside and out. Third fact that I want you to be aware of. If f of g, this is the composition. Let me just write it like that so no one mistakes after a multiplication. If f of g of x is continuous at x equals a, g of x is continuous at a, and f of x is continuous at g of a, then f of g of x is continuous. So we'll also be applying that from time to time. But that's just a fact that you should know. By the way, now I can do, we spoke about this before, but we didn't have the right language for it. Right now I'm going to use the proper language. BTW. We've had this for a while, but I think I just forgot to describe the number e and e to the x. So remember I said y equals e to the x, the most important function of all of mathematics. And now with the idea of limits, we know it's a continuous function, and with the idea of limits, we can actually talk about what e is. We can actually define e now to be the limit as n approaches infinity of 1 plus 1 over n to the n. Now that's something that from now on you should know. It's just a fact we know now. That's the way to define the exponential. And as I mentioned, this came from us actually considering, well, it actually came from Euler considering, that's why it's called E. The situation in which you are compounding something n times per year over the course of 1 year, and you are letting the number of times you compound it go off to infinity. The result is E. So if you deposit $1 into a bank account, where they're charging you interest on top of interest an infinite number of times in the year, at the end of the day, at the end of the year, you'll have $2.72. So it doesn't go off to infinity, your exponentials grow like that. Similarly, another way to define this is you can look at it as it's going from 0, and you just kind of change where the reciprocals are. That's also true. This one is more common though because it looks exactly like the compound interest formula if you remember what that is. And so e to the x you can describe as the limit as n approaches infinity, 1 plus x over n to the b. Now this is just something you're going to know. It's going to pop up at times where you're not expecting it to pop up necessarily. In fact, even in this class, there's a proof that I'm going to do where this is just going to come into play at this weird, opportune moment. And it's going to help us figure out a very important formula that we're going to use. And it's one of the formulas that, yeah, when a lot of people think calculus, that's one of the first things they remember from calculus. If they remember one thing from calculus, it's going to be that thing. And that's going to be true because this is true. It's going to be weird when you see it actually work out. I'll actually do that proof for you. Not the fundamental theorem. I'm talking about the power rule. Surprisingly, not a lot of people remember the fundamental theorem exactly. But the power rule, everyone remembers the power rule. Oh yeah, derivative of x squared is 2x. Derivative of x cubed is 3x squared. Like 10 years later, you ask someone, they'll remember that. But they won't remember anything else. Turns out we're going to use this to prove the power rule. You'll see it when it happens. It's going to be cool. Yeah, so I just want you to be aware of that. So that is pretty much how you want to think of E now and for the rest of your life. It's particularly important in Calc 1 and Calc 2. And as of Calc 2 and above, often a better definition. At the end of Calc 2, or at the beginning, depends on how your professor wants to construct it, you're going to do a topic called power series, and you're going to be able to describe the exponential function as a power series, and it's going to look like this guy. You don't have to remember for this class. I just thought I'd throw it out. So this sign here is a sigma. It means to sum. It means you're adding up a bunch of things that look like this for every n, starting at 0, then 1, then 2, then 3, going forever. Right? So this guy is adding up to 1 plus x squared over 2 plus x cubed over 6 plus x to the 4th over 24 plus keep adding things like that forever. It turns out it adds up to e to the x. That's going to be super useful in a lot of contexts once you pass it to. So right now these are just facts. They're things you should know, right? It's not something necessary that you have to figure out. They have been figured out, but you don't need to know how to figure them out. I'm not going to ask you, but at any given time, everything that I just said is just a fact you should know. Now I want to cover a fact that you should know, but there is going to be a computational side of it. It's going to be something for you to figure out, and I put it on the bonus of today's quiz. So in the bonus problem, I'm going to tell you how to do that now. So this is a very, very important theorem. Very, very important. I cannot stress to you how important it is, but you realize how important it is. For those of you who are going on in mathematics, or you want to do applied mathematics, or you want to minor in mathematics, and you're doing things like numerical analysis or something like that, you'll realize how important this theorem is. It's important for a lot of reasons. A lot of theorems that we use will also be using this. It is called the intermediate value theorem. So back on the quiz, when I asked you, how do you know that's the answer? You should have said, it's the intermediate value theorem. The intermediate value theorem tells me that this would be true. So the answer was yes, of course. And when you say, how do you know? The intermediate value theorem is how I know. Okay. So it's a very important theorem. On test 1, I'm definitely going to ask you a question where you're going to have to use this. On your final, I'm not sure, but I'd say chances are pretty good that you might see like a part of a question where you have to use this. It's not one of those things that's always on a final, but it's a very common thing to talk about because it's a very important theorem. And here is what the theorem says. If f of x is continuous on an interval AB, right? Meaning for all points in AB, if I take the limit as x approaches that number of f of x, I will get f of that number as the result, right? So it's continuous. On this interval, it has no breaks, no holes, no gaps, it's just going, right? And let's say f of A is less than n, some number n is just a number, which is less than f of B. Or vice versa. So if I plug A into the function, it's less than some number. And if I plug B in the function, it's greater than that same number. Then, here's a conclusion you can always make. There exists some number in the open interval such that f of c is equal to exactly that number n. And this is called the intermediate value theorem. It's basically the theorem that says continuous functions attain all intermediate values. What do I mean by that? Well, let's say here's my function, it's doing its thing. It's continuous, no breaks, no gaps, no holes, going from here to here. Suppose that's where A is, that's where B is, which means this is f of A, and this is f of B. Now someone can come and pick any random number they want. It doesn't matter what that number is. Pick a number in between these, called n. Any intermediate value. Then it turns out that there will be some input value in between A and B, such that the output of that input value will be specifically that number n. More specifically, that number is going to show up here in this example, right? You tell me an output that's in between two other outputs, I can guarantee hit that output with a continuous function. Because there's going to be no hole. It's not like there's going to be a hole here, so I'm not going to be able to get that output. I can definitely get that output. Right? Now, of course, it looks very straightforward when I draw the picture on the board, but this is something that you have to prove, and you have to be very careful and very delicate about it. It's a theorem, after all. But that's what it says. Continuous functions attain all intermediate values. Now, one way in which this can be important is when it comes to solving equations. Now, solving equations is a very important thing to be able to do, but not all equations are very nice. and sometimes they're very hard to solve by hand or otherwise. And sometimes it's actually impossible to solve them using the mathematics that we know about so far. And this theorem comes in handy in those situations and others. So let me give you an example of how you use this theorem, how you actually express that you're using the theorem. Any questions about the theorem, about what it means, what it says, what it's talking about? Very important theorem, intermediate value theorem. Sometimes I'll abbreviate by IVT, and you can abbreviate by IVT as well. So I'll know if you write IVT, you're talking about the intermediate value theorem. Here's an example where we can use it. So a root just means an x value that causes a function to be equal to 0. So this is basically saying this equation has a solution in this window, in this interval here. Now there is something, kind of like how you have a quadratic formula, there is a cubic formula. It's really nasty. I think like not many people have actually even seen it because it's just so hard to actually apply. But in general, cubics are kind of hard to deal with by hand. Sometimes you can factor them using long division, rational roots theorem, and things like that. But actually solving one, a general one with random coefficients, it's really hard. Unless you're a computer, someone gave you the actual formula. So one way to show that it has a solution is to find the solution, but for this one it's going to be very hard to actually do that. And so here's a way that you can know that a solution will exist. And after me going through this, you'll probably have some idea of what you had to do to actually answer that, or what the answer to the quiz question meant. So what you would do is you would set f of x equals x cubed plus x plus 2. Then you would go something like this. Note, if I evaluate the function at -1, what would I get? Well, I would get -1 minus 5 plus 3, right? In other words, I would get -3, and we can note that that is less than 0. Also, if I were to plug in f of 0, that's just 3. And we can note that's bigger than 0. So, it turns out, since f is continuous, how do I know it's continuous? It's a polynomial. It's one of the 6 fundamental examples of what it is to be continuous. Since f is continuous, and I saw that f of -1 is less than 0, and f of 0 is larger than 0, that means the 0 is like our n in the intermediate value theorem. There must be some c in the interval -1 to 0 such that f of c equals 0. And this c is the root. That's just applying the intermediate value theorem. Now, f is continuous because it's a polynomial. This means it attains all intermediate values. So if I know it hits values below and above 0, it will have to hit all values in between, which is in fact 0 itself. Right? So if I look at a little picture here, looking on the window -1 to 0, at -1 we were down here at -3, and at 0 we were up here at 3. It's a continuous function, which means it had to cross 0 at some point. Right? And that x value is going to be your answer. So that means this equation actually has a solution. So now, another thing, a lot of people always, who think about math, they always think about math, and I guess it's because of how teachers are, they always say, no, this is right or this is wrong. People kind of feel like, oh, there's always an exact answer. There's always an answer that we can get to. It turns out this is not always true. A lot of mathematics is about approximating, or give us a window where the answer is, because we can't really figure out what the actual answer is. And this is one of many things. You have things like Newton-Raphson theorem and other things like that, where we can kind of get a window to find out where the solution to some equation is, if we can't actually solve that equation itself. If we're in a situation where the function is actually continuous, we can use the intermediate value theorem. We can guess a window, do this check, and see if the answer is in there. And if the answer is in there, great. What we can start to do is start to narrow the window to try to get closer and closer to the answer. And normally if we get within some tolerance, we're happy. So this thing can be applied in a lot of more complicated numerical scenarios. But you just have to know how to apply it in a very basic sense. So for the quiz, a question I could have asked. So is cosine of x equals to x for any x value? Right? I could have asked you that question. Can you think of any x value where cosine of x is equal to x? Where's the cosine equal to its angle? Like, how do you even go about solving something like that? Can anyone think of one? I mean, sine of x equals to x, that one's easy, right? X equals 0. But cosine of x equals to x? Is it ever equal to x? Maybe there's no answer. But what I could do is this is just me asking, I did it the other way. Does x minus cosine x ever equal 0? That's the same question, right? So what I could do is I can set a function equal to this. And I can plug in some values where I know they're going to be above or below 0. So for example, I can find f of 2. 2 minus cosine of 2. That's definitely greater than 0. How do I know? It's a cosine. The maximum is 1. So 2 minus something that's 1 or less is definitely going to be positive. And I can look at something like f of 0. So that's going to be 0 minus 1. So that's minus 1. That's less than 0. And so what that means, there is some x such that f of x equals 0. There has to be, right? So even though I can't tell you what that x is off the top of my head, one, I do know whatever it is, it's between 0 and 2, and it exists, right? So I know the solution is out there. I'm not wasting my time actually looking for it or waiting on a computer to find it. Although a computer can find it's pretty easy, but yeah, in theory, so that's the intermediate value theorem. Sometimes you have an equation, it's very important you need to solve the equation, but you can't really solve it based on what you know so far. You can approximate answers, like just throw out a window, see if it works. That you might have some intuition behind it, and then you can use something like the intermediate value theorem, or something more sophisticated, but the intermediate value theorem is one of them, to actually check, is there an answer in this window? Yeah. What if I narrow it a little bit? Is there still an answer in this window? Yeah. Narrowed it a little bit. Okay, so you can kind of pinpoint the answer a little bit better. And yeah. So a lot of people think of math as this exact thing. It's not always exact. Sometimes you have to be able to guess, but you want to have your guess really close. Yeah, you have a question? Oh, this was on the quiz. I just gave those to you. It could be anything in theory. Yeah, any number where that's in between the two values, anyone can work. Yeah. Come again? It depends on the equation I wanted to solve. So the equation I wanted to solve has to equal 0. So one way to show it is show that I can get above 0 and below 0. But since it's continuous, it has to pass through 0. So that was it. Huh? So it depends on the situation. Usually in a test, I'll give you a situation. Is this ever equal to this number? And then you're going to figure out how to get above and below that number. So that's the intermediate value theorem. And you'll pretty much see a question like that, where I'm going to ask you, does this equation have a solution on this interval? Then you're going to test it, and then you're going to tell me yes or no, and then you're going to tell me, how do you know? And you're like, well, the function is continuous. And you justify all this. So for example, this you can say, oh, this is continuous because it's the sum of a polynomial and a trig function. And we have a theorem that says when you add two continuous functions, they're continuous. So we know this is continuous, so it will obey the intermediate value theorem. And so you just say, by the intermediate value theorem. So that's a nice thing. But the significance of this theorem, it's not really going to hit you until you're at some higher level mathematics, and then you're going to, oh, we can use that theorem! And then you're going to get so excited. Okay. That's all I wanted to mention for continuity at the moment. Now the next thing we're going to go into, I believe it's, yeah, I'm not sure what's actually. But we're going to talk about the precise definition of a limit. That's the next thing I want to talk about. Now the problems here to solve, they're kind of a little bit sketchy for the typical Type 1 student, but I'm going to try to make it as easy as possible to kind of give you like a template so you don't have to think too much. But it's going to involve you knowing how to prove something. I mean, using the intermediate value theorem is kind of like that as well, but it's easier to follow. So we're going to talk about the precise definition of a limit. The last thing I want to talk about before we get into the actual calculus. So, previously we saw that the limit as x approaches a of f of x equals L means as x gets close to a, then f of x will get close to L. Now I gave you this definition, and I believe even at the time, you can probably check your notes, I'm pretty sure, I described this as the fuzzy definition, the kind of intuitive definition that we can get a lot done with it. We've been doing a lot with limits just by this definition. But strictly speaking, it's very vague. Especially from a mathematics point of view. What about this is vague? See any cause for concern here? What's vague about this definition? Well, I mean, we have an idea for what happens at A already. That's just evaluating the function. That's not really, that's a different idea altogether. Limits doesn't care about being at A. It's not like it's something wrong with the definition. It's something that we specifically don't care about. But what makes this vague is the word close. That's very vague. What do you mean it's vague? Well, you know how some people can be talking to them, hey, what's going on? And they'll talk back to you and like, oh yeah, you know, I'm doing fine. And other people will come, hey, what's going on? They're like, yo, you're too close, man. Get out of my space, right? So it's like, for the first person, you're not close to them. You're not too close. But for the other person, you standing at that same distance, they're like, hey, you're too close, right? Close is vague because it kind of depends. It's a very subjective way to describe something. What some people think is close, other people won't think is close, right? So when you say, oh, it's close, close according to who, right? Like, that's very vague. What do you mean close? A half unit, 0.5? Do you mean 0.3? Do you mean 0.01? What do you mean when you say close? It's not very specific, right? So some people might say, yeah, that's close, but other people, that's not close. That's really far, right? So the close idea wasn't really good. It wasn't really precise. We want to talk about a precise definition. So now, basically, the math people want to take the word close and make the meaning specific so that every person is going to agree what's close or not. And you're like, well, if it's subjective, how is everyone going to agree on what's close or not? And, well, that's the idea. You make the subject choose. Let anyone choose what they want close to mean to them, and you're going to come up with a definition that's going to fit their definition of close, whatever they happen to be thinking in their mind at the time. How do you actually go about doing that? Well, here's one way to talk about that, making close precise so that anyone will actually agree. So here's the definition, the precise definition of a limit. I'm going to just write it down. It's something you should know. And then I'm going to explain it, maybe draw a few pictures, and then we'll do some examples. So, let epsilon be greater than 0. This is the Greek letter epsilon, lowercase epsilon. It just represents some number. We say the limit as x approaches a of f of x equals L if there exists some delta greater than 0, just another lowercase Greek letter, such that if the distance between your x and your a is less than delta, potentially they're not the same. They can never actually be the same. We don't care if x is actually equal to a. Then the distance between the f of x and the L value will be less than epsilon. This is how we can say close. And 7 billion human beings can come up with 7 billion different ideas for what close means to them. This definition will work for any human being who's happening to look at the problem right now. So, let's kind of explain what I mean. Epsilon is the tolerance. Epsilon is what the person who happens to be looking at the problem at the time says, I think that would be close, right? This is my idea of what's close, right? So someone can give you a number here. 1, a half, 0.00000000001, whatever. They can give you any random number. Any positive number, they say, that distance is what I consider close. And someone can say, well, this distance is close enough for me. And someone can say, this distance is close enough for me. They're going to give you some number, some distance, right? Now, here's what it means to say that as x gets close to a, f will get close to L. Meaning, if someone tells you how close they want the y values to get together, which is this, you can tell them how close you have to make the x values get together to achieve that tolerance. So let's look at some remarks here. Epsilon is a tolerance for how close the y value, or I should say the x value, we get to L, right? So it's a given tolerance. The delta is a response by you depending on epsilon. That will get the y value to achieve the above tolerance. Okay. So let me actually draw a picture. So this is just something we know, right? So we say, let me give you another way to write this in some shorthand here. And this is probably the one you can remember. Giving you some mathematical lingo here. A lot of it is the same, but you might hear me refer to it another way and other people refer to it another way. For all epsilon greater than 0, there exists delta greater than 0, such that if x is within delta close to A, then your f of x will be within delta epsilon close to L. And so this is probably what I would remember if I were you, because it's kind of shorter, less writing. And let me just introduce those symbols. Where this upside down A means for every, for each, etc. Right? So it's a logical symbol. So if you study logic at some point, you're going to use a lot of symbols for stuff. That's going to be one of them. It's a universal quantifier, it's called. There exists is a backwards E. This is called an existential quantifier. It means there exists there's at least one, etc. Right? So if you want to say something exists, it's out there. There's at least one such thing out there. You can put backwards E to represent that. And then you could say, for everything this is true. You can use upside down A to represent that. That's for all or for every. That's not really official. That's just me being lazy. Whenever I write that, I mean such that. Yeah. So to say this means for all epsilon greater than 0, meaning no matter what someone asks you about, there exists a delta greater than 0. So if they ask you, you can respond to them with another number, such that if your x is that close to A, your y value will be that close to L. So someone must say, oh, you know what? I think my y value should be within 1 unit close, and then I can respond. Okay, to get within 1 unit close, make sure your x values are within 2 units close. And then someone can say, no, that's not close enough. I want them to be a half unit close. Okay, to get it a half unit close, make sure your x values are 1/3 unit close, and then the y values will be a half unit close. So whatever someone says to you, you'd be able to respond to them. So basically the idea here, I probably want to do more space here. So copy this down. Here's the idea. Let's say this is, suppose this is our function doing its thing. And let's say right here, the point might not exist, but I'm just filling it in. So this is at A. And this is your L. Right? Now just by looking at this picture, we have the idea that oh yeah, just looking at this I can tell that the limit as I approach A is going to be L. As I get close here, it's going to get close there. But what does that actually mean? Basically what someone is going to say, you know what I think being close to L means? It has to be a distance of epsilon away. So someone is going to come and tell you, okay, I will give you this window, this tolerance. Get within 3 decimal places of this number, and I'll think that's close. Or get within 1 decimal place of this number. Or get within 1,000 decimal places of this number. So this is like you're moving up a distance of epsilon or down a distance of epsilon. So this number here is L minus epsilon, and this number up here is L plus epsilon. But that's their window that they allow you to get close, right? So everyone will have a different definition. It doesn't matter. It's going to be some epsilon. Close means this to me. You're within this window, or within that window, or within that window. Everyone's going to give you something. Okay, so what happens is, they give you some leeway. Now what you have to tell them is, okay, to achieve that leeway, just make sure that your x values get within this window. Right? So someone is going to tell you the green, you are going to tell them the blue, right? So this distance here is a distance of delta, and that is a distance of delta. So this would be A minus delta, this would be A plus delta, right? So as long as your x value is that close, it's some x value inside of here, you will achieve what you actually desire, right? So basically what you've done here is, should have done that in blue, but you've achieved a window so that once your x value is inside this window, your y values will automatically be inside that window. Now, if you make the window too wide, you can mess this up, right? Let's say you open the window like over here. Then that's not going to work, because someone can pick an x value right here, and look now, you're outside the window. You didn't meet their criteria for what needs to be close, right? So this window is too wide. So someone's going to give you a window for the y values. Oh, that's what it needs to get close to y to meet. You're going to give them a window so that as long as they make sure their x value is in that window, it will be in the window that they gave you in the first place. And then they're going to be like, yeah, that's close, right? Everyone's window is going to look different, but everyone's going to achieve it. So someone else might give you a smaller window. Oh, you have to get this close to the point. Well, what you would do is you would narrow your window. Okay, make sure the x value is in here, and I'll be inside your window. right? So a different person gives you a different window, you just make your window change to fit their window. And you want to not go too wide, because if you go too wide, you drop outside of their window, right? And then they're like, that's not close, that's way outside of my window, right? Okay. How do you do this? Am I going to have to do it 7 billion times for the 7 billion people who ask me? No. We are going to be able to find a function based on the given window that I can automatically just respond to everyone. So I'm going to find a way so that no matter what the window is, I can tell you a formula to calculate the window here that will get you close as you want. And that makes it precise. So let's do some examples. Now, here's how you know when you have to look at a limit in this way as opposed to the way that we've been doing for like 2 weeks now or so. It is going to say prove. Or they might use the word show. Or justify or something like that. They're not going to say compute. Right? If someone says compute the limit or calculate the limit, do what we've been doing. Just think of it the fuzzy way, do the plug-in, go through that strategy. But if someone says, prove to me that this is the limit, prove to me that you can really get as close as you want. Right? So prove that, and here's another way you're going to know that you're supposed to be doing this kind of idea. They're actually going to tell you the answer. So, A. Here are some problems that we're going to do. Prove that the limit as x approaches 4 of 3x minus 7 is 5. Right? So you go and you tell someone, yeah, as you approach, as x gets close to 4, 3x minus 7 is going to get close to 5. And they say, prove it. What do you mean close? Would you get within half the unit? Yeah, here's how. I'm proving it to you. Right? So that's the situation. For people who don't trust them. Now for us, we know we can just plug in and get the answer, but how do you really know? Prove that as x approaches 3 over 2 of that expression, the answer is going to be 6. Now, the kind of questions they're going to be asked, they're never really going to be really complicated functions like I was asking in previous quizzes, because as you'll see, this can get pretty difficult to prove for simple functions. Even this guy, this one is the most complicated one, and it probably looks a lot simpler than those. This guy's going to actually be kind of tough to get. So what we will do is I'll do A, and we'll stop. I'll have you try B on your own for Wednesday, and then we'll do C together on Wednesday. And after that, we'll kind of wrap up all the limit section. I'll tell you a few more facts here and there. In 15, 20 minutes, we'll be wrapped up with this kind of stuff, and then we'll move on to bigger, better things. But yeah, so let's see. If you tell someone the limit as x approaches 4 of 3x minus 7 is 5, and they say, prove it. Here's what you're going to do. So you want to know that you can get within their tolerance of close. So I'll probably do I'll do a slide discussion first, then I'll give you the template. So here's how you're going to be do the proof. Let epsilon be greater than 0. And sometimes people like to put b given. So let someone give me whatever epsilon they want. I don't care what they're going to give me. tell me any positive distance that's close enough for you. Right? What you're going to do is then choose your delta equals this thing. We're going to figure that out. Then, if x minus 4 is less than delta, if I get my x, the distance between x and 4 to be less than that number that I'm going to tell you, then your function 3x minus 7 minus 5, the distance between those two values is going to be ultimately less than epsilon. Now, this is stuff I'm going to have to fill in here. Okay. So now, how do you actually figure out what will actually get this to work? Well, here you go to the side. Go to the side and you do some scratch work. Okay, let's make sure that this works. How am I going to know what to pick here? Well, given since the distance between x and 4 is less than delta, and we want the 3x minus 7 minus 5 to be less than epsilon, what does that actually mean here? Well, 3x minus 7 minus 5, simplify that. What do we get? 3x minus 12. What can I do with that? Well, I can factor out 3, right? Well, hopefully you remember that absolute values can distribute across products, right? Now, absolute value 3 is of course 3. But now I see, look here. That guy is this guy, right? So this guy here, here's what I'd be able to say about it. This guy here, 3 times that, will be less than 3 times delta, right? Because this guy's less than delta. But I want that to be less than epsilon. This is what I want. So this means I can just solve my delta. Let it be epsilon over 3. So now what I'm going to do is I'm going to go over here, and I'm going to fill in epsilon over 3. So someone says, this is what close means to me. Oh yeah? Okay, make sure your x values are within a third of that distance, and you're going to get that. And how do you know? Well, they go here, and they try to check it, and they're like, okay, well this is going to equal that, which is going to equal that. Well, if this is less than delta, this is going to be less than 3 times delta. But if my delta is epsilon over 3, then that guy ends up equal to epsilon. So what ends up happening is my f of x minus L ends up less than epsilon, right? So if someone gives you a tolerance, give them a tolerance that's a third as wide. So if someone says, you know what's close to me? 30 units, okay? Make sure your x values is within 10 units. No, that's far. 1 unit is close, okay? Make sure your x values are within 1/3 units. You know? No. 0.1 is close. Okay, make sure your epsilon is between 0.033333 units, and you will get that. Whatever someone tells you, you can tell them how close the x values need to be to get their y values that close. So it's going to be close by anyone's definition. So now, and this is pretty much what our problem is going to look like. That's actually side work. So the template, and I'll talk a little bit more about proving stuff later, but here's how the template is going to be. So if someone asks you to prove a limit or show that this is the limit, here's the structure, here's the framework in which we're going to give your answer. Template. This is something that might need some time to sink in, so we'll talk a little bit more about it on Wednesday. If asked to prove limit as x approaches a of f of x equals L. Let me actually maybe color code these things a little bit, because you're going to actually plug these into the thing. So let's say my A is the red. It's going to be some number, obviously. And my f of x is blue. And this is L. Right? So if that's the question, here's how you're always going to start the problem. Here's how your answer is always going to look like this. Answer. You're going to say, let epsilon be greater than 0 be given. Full stop. The next thing you're going to write is choose delta equals blah. Now, that's something you need to figure out. Right? In the way that I kind of showed you. Force what you want to happen, kind of get your delta to slide in there and solve for the delta in terms of the epsilon. Then, if x minus the a, so you're going to take the number that was there, you're going to put it here, because that's a delta. We have, now you're going to write down your f of x minus, you're going to plug in the L, equals, you're going to do some calculations based on delta. Show that where that's an epsilon, and you're going to end the proof like that. Now, this here side work is, you're going to do some side work for this, and then you're going to just come back and say it like you always do. That was the answer. Oh, epsilon over 3, obviously. No, you went to the back room and you calculated it and you came out and say epsilon over 3. But yeah, that's your template. Then you're going to draw a little box right here, and you're going to shade it. And that's basically a symbol that means, oh, this ends the proof, right? So the proof is going to start here, which you can write PF. Right? So they ask you to prove a limit. You write proof. Let epsilon greater than 0 be given. Choose delta equal blah, something you're going to calculate to the side. Then if x minus a, you're going to write that number here, is less than delta, you will have that f of x you're going to write in the function, you're going to write in the L, is going to be equal to this thing, but by the time you calculate it, it's going to be less than delta. It's going to be within that window I was given. Yeah, that's right. Let that sink in. It's kind of a different kind of math problem, but that's the worst kind of proof you'll probably have to do. Yeah, try the example B, and we'll wrap up there. I have your quizzes to give that.